Imagine a world where a physical property, like the color of an object, changes depending on how you look at it. Sounds strange, right? But this is precisely what the Kochen-Specker theorem suggests about quantum mechanics. It tells us that it is impossible to assign definite values to quantum properties independently of how they are measured. In other words, the outcome of an experiment isn't just revealing a pre-existing reality, it depends on the measurement itself. This theorem rules out the idea of non-contextual hidden variable theories, which assume that quantum properties exist before measurement and are independent of the observer's choices. Why is this important? In classical physics, we assume that properties of objects exist whether or not we measure them. A ball has a definite position and velocity even if no one is looking. However, in quantum mechanics, the Kochen-Specker theorem proves that certain quantum properties cannot have predetermined values before measurement, at least not in a way that is independent of the measurement context. This challenges our fundamental assumptions about objective reality. For example, let's say we have a quantum particle and we want to measure its spin along different axes. According to classical intuition, the spin should already have a well-defined value in all directions, even before measurement. But the Kochen-Specker theorem shows that assigning consistent values across all possible measurements leads to contradictions, suggesting that the particle's properties are not predetermined, but are somehow influenced by the very act of measuring them. This paradox raises deep questions. Does reality only exist when we observe it? Is the universe fundamentally non-deterministic? Some physicists suggest that quantum mechanics hints at a reality that is not local and not independent of our interactions with it. Others argue that the result supports interpretations such as quantum contextuality, where measurement choices actively shape reality, or even many worlds interpretations, where different outcomes exist in parallel universes. Experimental tests of the Kochen-Specker theorem using quantum computing systems and photonic experiments have confirmed its predictions. For instance, recent quantum optics experiments have demonstrated contextuality, the idea that quantum properties depend on how they are measured, not just on the system itself. This has implications for quantum computing and quantum cryptography, where contextuality might be a resource for computational speedups. The Kochen-Specker theorem forces us to rethink what it means for something to exist in the quantum world. If properties are only defined when measured, what does this say about the fabric of reality itself? Is reality fundamentally interactive rather than objective? These questions continue to challenge physicists, making the paradox of quantum contextuality one of the most intriguing mysteries in modern science. The Kochen-Specker theorem states that non-contextual hidden variable theories, where physical properties exist independently of measurement, cannot be reconciled with quantum mechanics. This theorem mathematically proves that the outcome of a quantum measurement depends on the choice of other compatible measurements, contradicting classical realism. As a result, quantum properties cannot be assigned definite values before observation, challenging our fundamental understanding of objective reality. An electron's spin in the x direction does not have a predefined value unless measured, and its value depends on which other observables are measured simultaneously. Just like a word's meaning can change depending on the sentence it appears in, quantum properties are defined only in the context of a particular measurement setup. Contextuality in quantum mechanics means that the same observable can yield different results depending on the experimental setup. The Kochen-Specker theorem demonstrates that it is impossible to predefine values for all quantum properties without contradictions, meaning quantum measurements are inherently dependent on how they are performed. This suggests that measurement is not merely a passive observation, but an active process that determines the state of the system. In an experimental test of quantum contextuality, photons passing through different polarization filters exhibit measurement-dependent outcomes that classical physics cannot explain. Just as a person's response to a question depends on the phrasing and context, quantum measurements are influenced by the broader measurement setup. Experiments using quantum systems such as trapped ions, superconducting qubits, and photons have confirmed contextuality by violating classical expectations. These tests involve measuring multiple observables in different sequences and demonstrating inconsistencies with non-contextual hidden variable models. The results strongly support the view that quantum properties are not intrinsic but emerge through interaction with the measurement process. Using entangled photon pairs, researchers have shown violations of non-contextuality inequalities, reinforcing that quantum systems defy classical determinism. Just as different interviewers might get different answers from the same person based on how they ask questions, quantum systems respond differently depending on the chosen experimental conditions. The theorem rules out a large class of hidden variable theories that attempt to explain quantum mechanics through pre-existing, well-dedified properties. If non-contextual hidden variables were possible, quantum mechanics could be reformulated classically, but experiments consistently refute this. This implies that any hidden variable theory that aims to explain quantum phenomena must incorporate contextuality. Bohmian mechanics, a hidden variable theory, circumvents the Kochen-Specker paradox by allowing wave function to Specker paradox by allowing wave function-dependent non-local influences rather than assuming independent properties. Just like a book's interpretation changes based on the reader's perspective, quantum reality is shaped by the context of its measurement. Both Bell's theorem and the Kochen-Specker theorem highlight the non-classical nature of quantum mechanics, but in different ways. While Bell's theorem shows that quantum entanglement defies local realism, the Kochen-Specker theorem rules out non-contextual realism. Together, they establish that quantum mechanics fundamentally differs from classical physics, and any local, deterministic, hidden variable explanation is untenable. Quantum computers exploit contextuality to outperform classical systems, leveraging the measurement-dependent nature of quantum states. Just as a hologram appears differently depending on the angle of observation, quantum states manifest different properties based on the measurement framework. Quantum contextuality has direct applications in quantum computing and cryptography, where measurement-based quantum computation relies on contextual correlations. Unlike classical bits, quantum bits derive computational advantage from the non-classical relationships defined by contextuality. Contextuality also plays a role in device-independent quantum cryptography, ensuring security even if measurement devices are imperfectly characterized. Quantum secret sharing protocols rely on contextuality to encode and decode information in ways that are fundamentally secure against classical attacks. Just like secret codes rely on contextual relationships between words, quantum information relies on contextual dependencies between measurements. The Kochen-Specker theorem suggests that the classical concept of objective reality, where properties exist independently of observation, is incomplete. It challenges the idea that measurement simply reveals pre-existing values and instead supports the interpretation that measurement plays a fundamental role in defining reality. This aligns with interpretations of quantum mechanics, such as the relational or Copenhagen interpretation, where reality is shaped by interactions. In delayed choice quantum experiments, the outcome of a measurement seems to retroactively influence the properties of a system, defying classical logic. Just as the meaning of a work of art depends on the observer's interpretation, quantum properties emerge only when they are measured. The Kochen-Specker theorem raises profound philosophical questions about determinism, objectivity, and the nature of knowledge. If quantum properties are not intrinsic but defined by measurement, then reality itself may be relational rather than absolute. This idea has fueled debates about quantum realism and whether the universe exists independently of observation. Quantum Bayesianism, Chibiism, suggests that quantum states represent an observer's knowledge rather than an objective physical entity. Just as a story's meaning depends on the reader's interpretation, quantum mechanics suggests that reality depends on how we interact with it. Despite its strong theoretical foundation, the full implications of the Kochen-Specker theorem are still being explored. Researchers are investigating new quantum contextuality experiments, connections to quantum gravity, and how contextuality might play a role in biological and cognitive processes. Future quantum technologies could harness contextuality for enhanced computational and communication systems. Contextuality is being studied as a resource for error-resistant quantum computing, potentially improving quantum algorithm efficiency. Just as unlocking new dimensions in physics leads to technological breakthroughs, understanding quantum contextuality may revolutionize computation and communication.